Welcome. So in this video I want to look at inverse functions and review some of their properties. So let's start with a very simple example. So let's start with a function f of x, which is 2x, and a function g of x, which is half of x. And let's take some random number, so say x equals 3. And let's compute f of 3. So obviously f of 3 will be 2 times 3. So I want to illustrate this on the little graph here by saying that 3 gets sent onto 2 times 3 through the function f. And the direction of the arrow is important here because it says that f is applied to 3 to give 2 times 3. If I compute g of 2 times 3, well, that's going to be 1/2 of 2 times 3, and the 2's will cancel out, and I will get back 3. So g actually takes 2 times 3 and sends it back to 3. So I can summarize this by saying that g of f of 3, so if I compute f of 3 I get this, and if I do g of that I get 3 again. So g of f of 3 is 3, and really that's not because 3 is some special number. It would actually work out for any number x. So in general I have that g of f of x is equal to x. And I can illustrate this with a little graph here. If I take any x, I can compute f of x, and I do g of that, I get sent back to x. And I could also take any number x, apply g to it to get g of x, and f would send it back to x. So what I get from those two graphs is that f of g of x is x, but also g of f of x is x. So in some way, g undoes the work of f, but vice versa as well. So f undoes also the work of g. So we say that g is the inverse of f, but we could also say that f is the inverse of g. Now in general, if I have a function f that sends value in the set A to values in the set B, then if I have another function g that takes values in the set B and sends them to values in the set A, we will say that g is the inverse of f if g undoes the work of f. That means if f of g of x equals x, and if g of f of x gives us back x again. Sometimes we'll write g as f minus 1, because if we do that, these two equations can be written as f of f minus 1 of x equals x, and f minus 1 of f of x equals x. And the notation is there to remind us that f and f minus 1 cancel out each other. So it is an analogy to the notation that we use for real numbers. So when we write a times a to the minus 1, well, that gives us back 1. Now, given an expression for f of x, how do we find an expression for g of x? Well, let's go again through this little graph. It means that if I take a value x and apply f to it, I'm going to get f of x, and let's call that y. Now, because g is the inverse of f, if I apply g to f of x or y, which are the same, I'm going to get back x. So that means that if y equals f of x, then g of y equals x. So if I have this equation, I can get an expression for g by solving this equation for x. So we need to solve the equation for x if possible. Now that might not be always the case. It might be actually very difficult to solve the equation for x. So let's take a look again at the example we had in the first slide. So f of x equals 2x. Now how do I use this equation in order to find the inverse g of f? Well, based on what we said previously, I have to take the equation y equals 2x and solve that for x. And here it's very simple. We get y equals 1/2 of x. So that means that g of y is 1/2 of y. And if I'm not happy with having y as an input, I can use x instead. So g of x is 1/2 of x. And I can use the notation f to the minus 1 for g instead, and write f inverse of x equals 1/2 of x. Now, as a second example, take the function f of x equals x squared, where in this case the domain of f is the set of non-negative numbers. In this case, The range would also be the set of non-negative numbers because the function is x squared. So if I square any number, I actually get a number that's non-negative. How do I find the inverse in this case? Well, I take the equation y equals x squared and solve for x. So to solve for x, I need to take square root on both sides. Now, the expression I get on the right-hand side, which is square root of x squared, is not necessarily equal to x in general. It is in general equal to the absolute value of x. But in our case, because the domain of the function is the set of non-negative numbers, the absolute value of x is x itself because x is non-negative. So in that case, it means that the inverse function is square root of x. Now notice that if we would not have restricted f to the domain of non-negative numbers, f would not have had an inverse, since there is not always a unique x such that y equals x squared. For example, if I take the equation 9 equals x squared, well, in general it has two solutions, 3 and minus 3. So g would not have been a function in this case. We could have called it a relation because g would have sent 9 to both 3 and minus 3 at the same time, but clearly it would not have been a function. Now, if we look at the graph of f and g, you can see that the graph of g, or the graph of the inverse of f, is a reflection of the graph of f across the line y equals x. Now, that is not a coincidence, and let's see why. Remember that, once again, because f and g are inverse functions of each other, a gets sent to b through the function f, but then b gets sent to a through the function g. So if I have the graph of f and a point AB on that graph, well, BA will be a point on the graph of g, or on the graph of the inverse. Once again, because b gets sent onto a through g. Now, if I take a point AB and I switch the x and the y coordinates, it has the effect of taking that point and reflecting it across the line y equals x. So if I take every single point on the graph of f and reflect them across the line y equals x, I'm going to get the graph of the inverse. So that's why we say that the graph of the inverse is a reflection across the line y equals x of the graph of f. Now, given the graph of the exponential function, how can we graph its inverse? Well, all I need to do is graph the exponential function here in blue, and that graph should be familiar to you, and you reflect it across the line y equals x, and therefore you're getting this graph here in blue. If I want the equation of that curve, all I need to do is take the equation here, y equals e to the x, and switch the roles of x and y. Therefore, I'm going to get x equals e to the y. Now, because this curve is so important, we have given a name to the function that represents it, and we've called it the natural logarithm. So we say that this curve is y equals ln of x. Now, I can get relationships between e to the x and ln of x by taking the standard relationship that hold between a function and its inverse. For example, take this equation, f of f inverse of x equals x. Remember that this is true because f inverse undoes the work of f. Well, if I replace f by the exponential function and f inverse by the natural logarithm function, it means that the exponential function applied to the ln of x, in other words, e to the ln of x, gives back x. So e to the ln of x is equal to x. Similarly, if I take the equation f inverse of f of x equals x, that translates into ln of e to the x equals x. Here's something very simple we can also notice. The curve here goes through 0, 1. So that means that this curve goes through 1, 0, because all you need to do to get the coordinates of this point is to switch the coordinates of this point. So that means that e to the 0 equals to 1, because 0, 1 is part of the curve that represents the exponential function, and therefore ln of 1 equals 0. We can also notice other relationships when looking at the behavior of the exponential function when x is large and negative or large and positive. As x approaches minus infinity, e to the x equals 0, because the x-axis is an asymptote here, which means that by reflecting that part of the curve across the line y equals x, I'm getting that part of the curve here. So that means that the y-axis now is an asymptote here. And in other words, we have that the limit as x approaches 0 plus of ln of x equals minus infinity. And similarly, if I take this part of the curve here and reflect it across the line y equals to x, I'm getting this part of the curve here on the curve y equals ln of x. And that means that the limit as x goes to infinity of e to the x equals infinity, because as x becomes large and positive, the y values are getting also large and positive. And therefore, over here, it means that when x goes to infinity, ln of x also goes to infinity. Finally, if I take 2 points, okay, on the graph of the exponential function and the graph of the logarithm function, such that a prime is the reflection across the line y equals x of the point A, and I draw the 2 tangent lines here, the slopes of the tangent lines will have a relationship. If I want to compute, let's say, the slope of that line, I'm going to do the rise over the run. But because the coordinates of any point here on this curve are the coordinates of those points here, but with the coordinates interchange, it means that the rise over the run here is the inverse of the rise over the run there. In other words, the rise here would correspond to the run there, and the run would correspond to the rise there. So that may sound a little bit complicated, but if you think about it, that implies that the slope at A prime is the inverse of the slope at A, because the roles of x and y have been interchanged when we reflected that graph across the line y equals x. Thank you for watching.